a faculty colleague, Abhishek Chandra, in computer science, and as usual, the set of graduate students who make it all happen. Okay. So for today, what I want to do is give you Cloud 101, things that most of you know. How many of you know about cloud computing? A little, sort of at least the buzzwords. Okay, about half. Or so I'll review those buzzwords with you and say what I sort of think they mean, and then sort of talk about cloud limitations. So what are some new problems we might want to look at with the current cloud paradigm? Okay, and then present two different ideas, although they're synergistic, that address some of those limitations, and also suggest the kinds of applications that might be better suited for our new sort of approach than the standard, what I will call centralized cloud. And then I'll sort of wrap up after talking about that. And our two ideas are what we call a proxy network and something we call nebulas. Unfortunately, we came up with the term, along with several other groups, fairly similar timelines. So there's open nebulas, and I think there's also nebulas. We are another nebula. That could change. So we mean our nebulas, if you know about other nebulas. Okay. And feel free to ask questions, interrupt, shout out. Okay. So there's a lot of discussion about what cloud computing really means, although there seems to be some emerging consensus about the cloud ecosystem. And so I'll put my version of that, adopted from Dennis Gannon in 2009. There seems to be agreement that at the bottom you have something like infrastructure as a service. This gives you the most control, effectively, over the environment. And you get to program the way you like. So this would be things like EC2, for example, where you have more direct control. Harder to program, low level, but you have more control of resources. Moving up the stack, you have things like platform as a service, where you have a higher level programming abstraction, perhaps more limiting in a sense of what you can program, but it's an potentially easier to use environment. And it hides more of the details of the infrastructure. So things like Azure from Microsoft and Google App Engine from Google. And then at the very top, you have software as a service, things like Google Spreadsheet, Google Mail. These are things you typically interact with as more of a client. You don't get to inject very much content or very much sort of applications into. You sort of are more of a user of them. And in many instances, these are actually these can be layered directly, which has implications for security and other things, which I won't talk about today. And then a completely orthogonal view of cloud computing is really the kind of transparency you get by parallel frameworks. So it's also very common to say, I've got MapReduce, the MapReduce paradigm, running on a cluster, and I'm going to call that a cloud, because user can run this and not have to know very much about what's happening under the hood. So there's another kind of use of the term cloud that tends to refer to those kinds of things. And in thinking about all of these different cloud sort of examples, what's fairly clear is a set of properties that most people agree represent cloud computing in one way or another. So this ability to scale up or scale down on demand. So my application needs more computing. It can acquire more, in the case of EC2, more virtual machines. In the case of Azure, more web roles. Various ways this is realized. In the case of Gmail, we simply get as much storage as we need. We seem to, whatever our needs are, it grows to accommodate that. And if we start deleting stuff, then our capacity, our scale goes down, and that's fine. Further, these things are remote. We don't know where they're executing or being hosted. That's another core property. So sort of thin client model, we're here, and all of our stuff is out there. Somewhere we don't know. Clouds, particularly pay-per-use clouds, have some sort of notion of performance. Okay? When I'm willing to outsource my computing or data, I expect some kind of performance in terms of access or execution. There's emerging things like quality of service, so that is just starting to get out, to sort of get released. But if I'm paying, I expect some kind of performance. And transparency, I don't know where things are. Okay, I don't know where computing is, I don't know where data is stored. So those are some core properties. Okay. So the standard cloud we might, and there's many ways to sort of try to represent this. I like Ian Foster's way of representing it as a cauldron, okay, being heated up by all the wonderful resources that might be available. And into this cauldron, we pour data, okay. In Ian's case, it's likely scientific data, okay. It could be commercial data. We sprinkle in algorithms, code, computations, okay, and out pops out results, okay. So we ladle out our results, okay, and all of this is achieved by virtue of storage and computing that is sort of infinitely available in this cauldron, okay. But what is attractive about this is essentially the co-location of computing and storage, okay, in this abstraction, okay. So that's the standard cloud, and it has a number of very strong appealing features. So you have a strong locality between data and computing. We pour them into the same infrastructure, and that's wonderful for things like analytics, where I just want to churn on the data, look for insights. Another very powerful benefit of this is that the cloud represents a novel sharing platform, both for data and for applications. So I might have a massively parallel multi-user game, and the common state that that game requires can be stored in a cloud. Okay, so it's a place to store state of applications. There's another emerging benefit of the cloud, and I'm thinking of the University of Washington CloudView project, where as soon as we start to deposit data and computing in a cloud, and therefore services, it becomes feasible to think about building on top of those services with new third-party services. So an example that they give is if I've got Flickr data poured into a cloud, one can imagine third parties building services to index that data, to do content-based search, layered on top of those things, and adding value to that data. So that's kind of an appealing notion, a sort of a application sharing platform as well. Okay? And so this locality and sharing, in addition, the economic benefits are really what you get by consolidating. Okay, so we bring things together, and that enables us to share, exploit locality, and get benefits of economies of scale. Okay, and a final, I think appealing aspect of the cloud is the abstraction it gives you, that you connect to it, you pour into it, and you collect from it. Okay. So this is obviously attract a lot of interest and have a lot of people excited. Okay, but removing ourselves from the cauldron and the hype and all the things that seem exciting about it. So we ask ourselves, what is really going on? Okay, what is the cloud really trying to do? And in some sense, it is really trying to centralize and tame a distributed world. Okay, and what is distributed? Data. Okay. Everyone's a generator of data, from blogs to Facebook pages to applications, generating data to instruments. So data is everywhere. Additionally, users are everywhere. And now users are connected all the time with mobile devices. Users are everywhere. And a third element is that clouds themselves are distributed. And I'll talk a little bit about that. Okay. Here's a cartoon generated by my grad student a day before I left. It said, draw me something, sort of show that the players here. So we're showing a couple of different clouds, actually vendors here. Got a data source here, and see a user there. And so this user might have extremely good connectivity to a particular cloud, maybe very close to that cloud, and therefore can interact with that cloud fairly effectively. On the other hand, this user may be far away from another cloud and have very poor locality with respect to that cloud. Okay? Similarly, for data, we might have very good connectivity between data source and a cloud, so we have a very good pathway to move data into the cloud. On the other hand, maybe we don't with respect to another cloud. There's no guarantee that it's going to be efficient to move data from here into that cloud, okay, or desirable. In addition, we're going to talk about locality between clouds themselves. So when I say clouds are distributed, there is not one cloud, okay? There's many clouds. And suppose I need to couple the capabilities or resources of multiple clouds together. Okay, and we'll talk about why that would be. So it might be the case that certain clouds have, very, I guess a solid line might represent very good connectivity, yet other clouds have very poor connectivity with respect to each other. That is, the cost of maybe moving data between them might be good or might be very bad. Okay? So what I've hinted at the previous slide is there may be some bottlenecks with respect to users and the cloud, with respect to data and the cloud, and with respect to clouds themselves. Okay? So our idea is somehow, because and those bottlenecks arise because of the natural distribution of things. Data is everywhere, users are everywhere, and so on. And understandably, the cloud has tried to tame that. But can we think about ways to make the cloud itself more distributed? Okay? Can we move it closer to the data? Okay? So can we expand the reach of the cloud so it actually is close to the data sources? Can we somehow move it closer to the user? Okay? Can we move it closer to other clouds? And I say, move in quotes because we're talking about providing that illusion, okay? Or providing a notion of performance, that somehow it's closer in terms of network performance, for example. Okay? Well, how are we going to do this? Clouds are fixed things. They run in data centers. And we're not going to pick up Microsoft's data center and sort of drive it over to where Amazon's is. Or we're not going to have all the users get in a bus and drive to an ISP that happens to be near one of the cloud data centers. So our idea is to leverage work that we've been doing over the years in basically edge computing. Okay, grid computing is one example. Peer-to-peer computing is another. So there's a large number of edge computers around on your desktop and ISPs all over the place. Okay, and those edge computers have lots of resources, as been demonstrated by various P2P projects and at-home projects. There's other types of edge computers. There can be commercial commoditized edge computers such as CDNs as well. In this talk, we're not going to necessarily advocate a specific model for edge computers, but we're going to probably be thinking more about volunteers. Okay? And we'll talk about how we can use volunteers or edge computers to give us this set of features. Okay. And I'm going to do so in talking about two different projects. One is somewhat less disruptive. It doesn't sort of alter the cloud paradigm. Okay, it sort of augments the cloud paradigm. I'll say that's somewhat less disruptive. And the other is more disruptive, which is to say, let's just build a different cloud. Let's refactor the cloud to be more intrinsically more distributed. Okay. And both of these will take advantage of edge computers. Okay. So the questions up to this point. Does everyone understand a little bit about the cloud model? Centralized, maybe a few data centers, but largely centralized. But the world is distributed, and that introduces other bottlenecks. Okay, but the centralized cloud model might not be the best way to solve. Okay, and hopefully that'll become more clear as I go through. Okay, so let me talk about the proxy network. And the goal here is to enable locality that the cloud doesn't enable, which is between a cloud and an end user, okay? And also between different clouds by exploiting edge nodes. And first, so I think it's pretty clear what we mean by this. So I've got a user that's interacting with a cloud application, whether a mobile device, a desktop, and they want this sense of good performance. They want good performance out of this, okay? But the cloud is somewhere else that's not guaranteed. Why do we want cloud-to-cloud locality? Why is that important? And this is where I'm going to sort of suggest some sort of trends. So if you look at the cloud landscape, and when I say cloud landscape, I'm probably generalizing a little bit. But I like to think of clouds as not necessarily what Amazon tells us they are, but clouds could be, they're outsourced third-party resources that provide value, okay? And we don't know much about their internal structure. So we could have data clouds provided by various vendors, various application groups, various groups. We could have compute clouds, service clouds. Increasingly, we're seeing clouds emerging that differ in terms of non-functional attributes. So clouds are going to emerge that offer lower cost or different types of SLAs or different kinds of reliability. It's very plausible to imagine this is sort of where things are going. Okay, there will not be one cloud. There's just an array of clouds offering different things. Okay, so we believe no single cloud model is going to be rule the day here, and therefore new distributed models make sense. Okay, that is, there's value for applications to consider utilizing more than one cloud, and they may in fact have to. Okay, and that's what we mean by cloud-to-cloud locality. So let me give you some examples. It's easiest to think about this in terms of data. So I want to analyze or process data that happens to be stored in different places, in different data clouds. Okay. So maybe I want to do distributed data mining on data that is stored at, say, NASA sites or NOAA weather data, and combine that somehow with data about commodity prices located in a different data cloud. Or scientific workflows. I have a data cloud that has GenBank data, or GenBank data, and I want to combine that with BLAST. Maybe that's running in a different compute cloud or a compute cloud, and then somehow I want to correlate that with data in PubMed, which is running in yet another cloud. Okay, and I somehow want to integrate this together. Or I want to mash up data from Google Earth and maybe CDC pandemic data sources. Additionally, I might want to run these parallel frameworks across multiple clouds. Why not do MapReduce or other parallel frameworks across data that happens to be in different places? Why do I have to pour it in one infrastructure to do that? The data might have to stay distributed. It might not be able to move it. It may be too big to move it. Or ownership might prevent me from doing that. Okay? So taking this all together, we think that it may become important to start dealing with the fact that clouds are isolated islands, but applications might want to couple them together. Okay. Okay. Sounds like an interesting idea, and we've tried to do this, but we quickly realized that there's some problems. Clouds don't really care about each other, and they don't really care about the end user. They're sort of about internal optimization, right? And the way you currently interact with a cloud is client-server, okay, or HTTP, web services. So suppose this user, I guess it's a scientist in this case, wants to grab some data from a data cloud S1, do some computing on that, and as a result of that computing, send that data to S2 to do further computing and get an answer back. Okay? So this is what the user has to do. Make a request to S1, and it's deliberately slow, because maybe this user is not well connected. Okay? Gets the data, computes, maybe that takes a while. Okay? Then sends that output to S2 to do something else, another stage, and gets an answer back. Okay? So this may be a fairly slow process. A lot of data movement back and forth. Maybe this user is not very well connected. Maybe it's a mobile user. Okay. And so what that exposes is a number of bottlenecks. Okay. Potentially network bottlenecks and computing bottlenecks for certain types of applications. And so our idea is, can we put another layer between, say, end users or end user applications and cloud resources that can alleviate some of the bottlenecks? Okay. And we call that a proxy network. It's not a new idea. Proxies have been around a while. But we're interested in the different roles proxies can play in enabling user and user applications to more effectively utilize clouds or multiple clouds. And so we have a couple of actors inside here. We have proxies themselves and what we call entry points. Entry point is a proxy, but it is one in which an application gets entry into the network. So an application or an end user has to first contact an entry point to acquire proxy resources. It's just their entry point. Okay. So we then think about applications potentially as containing sort of some of all of these. So Blue application consists of some components running at, say, a user's location, maybe including the user, some number of proxy resources, and then maybe some clouds that user is accessing. Okay, and so how can the proxy help? Okay, so this blue wants to access the blue cloud. How is the proxy going to help? Okay, so we want to exploit the diversity of proxy nodes and their resources to do this. Okay, so we showed you this user application going directly to S1, then directly to S2, doing some computing, and maybe there's a variety of bottlenecks at this user's location. So instead, what this user can do is say, is there a proxy that can do better than that? Is there a proxy that might have better connectivity to S1 and S2 and have much faster network transfer? So pictorially there is, and we've done it. We locate a proxy P that has much better network connectivity to S1 and S2 and can move the data much more effectively. Additionally, what we could also have done is we can, this node also may have greater compute power potentially than what this user has, and we could even compute in the network as well. That's another option. Okay. So what's exciting about proxies is it's not a new idea, but most people look at proxies, either they simply do routing or they simply do computing in a grid sense. We are thinking of proxies that can do any of a variety of roles, perhaps as many as 4 roles, and how to have those roles sort of in effect together. So what we just illustrated was a proxy that could serve as a client to a cloud on behalf of a user. Okay, proxies can route data to other proxies. Proxies can do some in-network computing, like grids in a way. A real benefit would be a proxy that can do data operators, such as compressing or filtering data, so you have less data flow back to maybe an end user. Okay. Proxies can also cache data. It's notorious that getting data from S3 and Amazon is fairly slow, so once data is retrieved, maybe you want to actually cache that in the proxy, and maybe multiple applications can actually share that data. Okay. So we're really looking at how do you combine these features together to get much bigger bang for your buck in terms of performance. Okay. Before I show you a couple of simple application scenarios, so we have a networking faculty here, and networking is a very, very important benefit of the proxy. Let me tell you a little bit about some measurement studies we did. Okay, so I drew you this cartoon of this proxy somehow had this magical, faster network path to the cloud or to some remote entities. It turns out that there was a lot of opportunity for that. So what we did is we did extensive study on Planet Lab, where we have hundreds of wide area network nodes available to us. So this is just a microcosm of the internet. Okay, and so it's sort of known that. Oh, I better get rid of that. You don't want to see about our arguments about furloughing. You may have your own arguments. Okay. So it's well known that there are better paths in the internet. This is work. This is sort of been sort of published earlier. But we wanted to quantify that and show, can we exploit that to our benefit? So what we're really showing here is just a few of our myriad of graphs showing that proxies can accelerate TCP bandwidth, UDP bandwidth, UDP delay, and or improve UDP jitter. So whatever's important depends on the application, of course. So if my application is moving lots of data to and from the cloud or within various components, TCP bandwidth, I want proxies that can accelerate that. If I am perhaps delivering data for remote visualization, maybe movie making, maybe jitter is really what I want to optimize for. And so the solid lines represents we have many such graphs, but each one is sort of the solid line represents a direct path between, say, a node and a cloud. Okay. These nodes up here show what would happen if I use various proxies to act as intermediaries. And so we can achieve a number of things. We're showing proxies that achieve much better performance, but also, it's really hard to see this, I apologize. If you follow the shapes, these proxies are also fairly stable. So over time, they give you that bandwidth acceleration. It's not just a one-shot. So of course, what you want to find is proxies that are better and that benefit's sustained. So maybe I need to do an FTP or grid FTP between two sites. These would be good nodes to sort of use in the middle. Okay. And so on and so forth with the other measurements, with the other metrics. Okay. So these opportunities are out there. This is a graph, I think, just showing TCP. And notice on the y-axis, we're measuring or showing the number of alternative paths that improve TCP performance. And it's times 10 to the fourth. Okay, so there's many, many paths that give you, over time frames, an acceleration of at least 0% over standard direct TCP, at least 10%, at least 15%, at least 25%. So I can't quite sort the colors here, but this tells you how many nodes on the order of 10,000 can give you acceleration at least 0% or at least 10%, or I guess 25 is down here. So this is a pretty big number. So it's at least 10,000 nodes can give you at least a 25% boost in TCP. That's more or less sustained over a period of time. Okay. And some of that acceleration is significantly large. Here we're showing for 3 different communicating endpoints, users and clouds, the intervention of proxies for the 3 different paths. And a big circle represents how many proxies could accelerate that, okay, communication in terms of TCP. And where it sits, how much improvement is sort of seen on the y-axis. So something up here, the higher and bigger, the better. So we have a certain large number of proxies in here that can accelerate communication as much as 50 or 60%. Okay. So there's some tremendous opportunities. Okay. And I just want to show a quick, not even really a demo, how do we get this information? Okay. And so we have a tool that a grad student has developed, and you can run it yourself, called the Network Dashboard. And we're building APIs to it for various collaborators who want this information. Let me just see here. So this is the tool. So he's monitoring a large number of Planet Lab nodes all over the world. And it shows you opportunities. So let's say I want to communicate. I want to know tell me about the path between Purdue and, I don't know, this PL is, not sure where it is. Poland, okay. All right. So, I go direct from, what did I pick again? Poland, Purdue to Poland. The measured bandwidth is 221. This tells me how many proxies could do better if I were to use them as intermediaries, and it plots over time what that performance would be. Okay, that's picking TCP. I could look at UDP if I want. So let's suppose what I'm really interested in is I have a UDP application. No UDP nodes. Okay. Okay, that wasn't very good. Let's say UCLA to Williams. Oops. Again, it'll tell us which TCP nodes, and it will show us over time which ones are better. For TCP, for UDP, he must have shut off the UDP in jitter. Okay. But you can run this dashboard, and it will show you historical trends and relationships in terms of network performance. And this is the data we're sort of showing you. But the exciting thing is we want applications or infrastructure to be able to use this information dynamically. Okay. And let me just show you a couple of different example scenarios in which we use this information. So this is just a very fun, very basic, just to get a feel for what opportunities might be. So we created a very simple image processing application that essentially distills images. And the images are stored out in an image server in the network. And the end client says, I want you to distill certain images and deliver them to me. Okay? And so the image processing cloud would then pull them from the image server, do the operation, and deliver them. Okay? So then we said, well, there's some network paths in here, to pull images this way and then deliver an output that way. Suppose we insert a proxy network to try to accelerate those communications. Can we, how much better could we do in the end-to-end time the client perceives? So it's all about, in this case, client says, click, do this for me, and I want to get my image back. I want to get an image in my hands. How long does that take, and how much faster can we do it with these proxies? And what we determined is that, and we varied lots of things, so we can vary where we put the image processing cloud, and these just represent different network locations. We can vary where the end user is, and we can vary where the image server is. And so in this graph, we fixed the location of the end user and the location of the image server. And the X's that you can't really see very well are what, if I were to use the non-optimized workflow, the non-proxy, what performance I get. Okay. So low is better. We're showing end-to-end time. And the red, which I've circled or hard to see, are dots. These represent when I insert a proxy or use the proxy network. This is the time the end user sees. Okay. So quite a few proxies deliver better performance, not always. Some of them quite dramatically. Lots of proxies, significant performance gap compared to the direct not using proxies. So there appears to be, this is just sort of a application of that data. Okay. And finally, let me say a little bit about montage. This is an application near and dear to some of our hearts. It's a large, complex workflow application. And there's lots of communication in montage. You have to pull images from Sky Survey and build and process that through this workflow to construct image mosaics. Okay? And the details are not critical for today, but only that there's a lot of data flow that goes on in montage till you get a final pretty image of mosaicked sky. Okay? And we thought we need to do something real to show we could benefit scientific applications, which is one of our primary interests. So we set up a sort of montage framework where, we pull data from Sky Survey, and the data is pushed through this montage workflow. And then the output of montage, the beautiful image you normally see, can go either to a standard desktop or, just for fun, how about a mobile phone, okay, as a test. Okay? When the data goes to a mobile phone, what we need to do is the proxy has to do some computing on the image. It has to distill the image so it's of the right scale for the mobile phone. So this is an example where we show how we can use proxies to do that kind of thing. But there's a lot of data flow in the montage, out of montage, and within montage. Can we use proxies to accelerate montage? So we're showing you we've broken into 3 pieces. So to get data from the Sky Survey into montage, into the compute nodes, the first stage of the computation, we use proxies to do that, to accelerate communication. And we're just showing 4 of those proxy nodes and how much they speed up that communication of just downloading the image data from Sky Survey, okay, to wherever you're going to do the computing. In this case, we're computing using some nodes in Planet Lab itself. Okay. Showing it for various image data sets that we can pull from the Sky Survey. So we can get speed ups almost, as high as 1.8, just for moving data for that first phase. And that data is very large. You might be downloading thousands of images. So we can get the data into montage more quickly into the actual pipeline. We're very early in this, but there's opportunities within montage itself between the stages. Once we compute data, it goes to the next stage. So we also inserted proxies between various phases. And we're showing for 2 phases, we're able to improve or speed up the communication by 24%, in one case 42 for another, between these different montage. These are just montage phases. Okay? And that was pretty exciting. So intra-application, we can also improve performance by inserting these things. Okay. And then the final thing we did is, okay, we have the answer, and we want to deliver that to the end user who wants to visualize the actual mosaic. So this is an Android phone, an Android emulator, and so this is actually a screenshot of montage output on the Android phone. So we have different classes of users increasingly that want to interact with the cloud or scientific applications in the cloud. Mobile user and a desktop user. And then we just played around with various things we could do. For the desktop user, we have compression to get the data there more quickly and then decompress. That's pretty standard stuff, but this is just an illustration of the kind of specialized processing proxies can do. And if we compress, we can save some time for bigger data sets. That's not surprising. It's just illustrating one of the potential optimizations. Okay. For the mobile user, we have to do distillation, and not surprising, if we do distillation, we certainly save a lot of transfer time. It's lossy, so that's not too surprising. But again, it's faster, and it's actually a requirement. We have to do this for the mobile user. Okay. Yeah.
Going back a few slides where you get the data for montage in the first instance and then inside montage.
Mm-hmm.
So I noticed that there's a kind of a trend towards lower, in the slide before this, there's a trend towards lower fluctuation. I know that the data size is not as relatively small, but is that something you agree with as a trend? And what's that saying about the networks, the proxy networks set up? Related to that is the efficiency that we saw in the next slide. Is there a input size dependency there as well, as in, does that tend to decrease as you go to larger?
That's a great question. We don't yet know. We don't yet know. Clearly, how dependent on the benefit is to data size is something we're currently looking at. There's a lot of variables in the network. It's hard to answer that. But that's a great question. So yeah, it does appear to be across different proxies more stable here, but the magnitude is uncertain as to, it looks like there might be a little bit more speed up here. It's hard to say. We're still evaluating this. Yeah. Okay. So our current status on this project is we're currently building it. We're deploying the proxy network and providing services that let applications take advantage of it, to query, to identify nodes that could improve their performance by optimizing both network and communication, and also in-network computations, with the good graces of NSF. Okay. Let me talk about, not a ton of time left, a project that's a lot of fun, actually, and it's pretty early. So this is disruptive, and disruption is also a lot of fun. We presented this at Usenix Hot Cloud and got a lot of interest from industry. So nebulas. So this is this notion of let's stretch the cloud out to be closer to the data and even to the user, okay, to gain additional localities that centralized clouds might not give us by using sort of edge nodes. Okay. And as a backdrop, as I stated earlier, so the cloud hides the details of the service deployment, okay, from the user, and the users are way out on the edges. But the current cloud model, as I've said, is largely centralized data centers. Maybe a few of these, but effectively centralized. For those of us that have done distributed computing on thousands of nodes, 5 data centers is centralized. Okay. Right. Okay. I've said this already. So we have a few data centers, pay as you go, some guarantees. That's important to acknowledge, because it's centralized in a data center. They can probably put bounds on performance, and that's a good thing. Okay. So this addresses the comment at the beginning is, so that's what we understand as a cloud, and we can sort of accelerate the cloud using proxies and things. But we then say, are there services that are just not going to fit this current cloud model well? Are there things that this doesn't do well that we should maybe be thinking about, or other applications that might not fit this model well? Okay. So we've come up with a couple of different classes that have different kinds of localities that may not fit the current cloud particularly well. One is we have large distributed data sources that perhaps are dynamic and changing. And it just may not be cost effective to move all that data into the cloud, especially if that data is dynamically changing. Okay? Instead, what we want to do is stretch the cloud so the computing is near the data. Okay? And I'll give you a simple example from the internet space, blog analysis. I've got thousands of blogs all across the internet, and I want to analyze those blogs, look for interesting things. Increasingly multimedia, all kinds of interesting content. I want to see what's going on. I want to do trend analysis. So it might be pretty expensive to move the entire internet's worth of blogs into a central cloud to look for things. So instead, what I would prefer to do, perhaps, is find computing resources that might be actually physically close to those data sources, okay, in network distance, and compute closer to that data. So that may be one class of application, prohibitively expensive to move the data in the cloud. The second class we call experimental services. So you're thinking about deploying a community code or a service that you think lots of people are going to want, but you don't want to have to pay for it until you know it's going to be of interest. Okay. Further, you might want to debug it and see how it works at scale. Okay. So you don't want to have to pay for Amazon resources to do this. You want an experimental platform that you can test on-demand scaling and see whether people are going to be interested in it. Okay? So as a computer scientist, one of the things I worry about when I'm program chair is, do I have a unique set of papers that I have to evaluate? And I might want to know, are there overlaps with prior publications, subtle overlaps, some kind of overlaps, okay? And I get together with my colleagues, and Shantanu been program chair, and maybe some of you have been as well, and we said, this is a great idea. I want a service where I can inject my stack of papers, and out comes out, 5 years ago, this piece of the paper was published. So I might like a cloud service that could pull data from various archival places, Usenet publication, ACM, IEEE. And so I would just inject my papers in there, and it would do an analysis. And the more program chairs that did this, it would have to scale out to accommodate that. Okay? But I'm a computer scientist. I don't get paid very much, relatively speaking. And I don't want to pay for this. I just want to see whether this is a good idea. I want to deploy it and just see. If there's English professors, I apologize profusely for that comment. Okay. And here's one's a little soft. Shared public services. So you develop some personal application that you think is really cool, and you want to make it available to everybody. Okay. And you need resources to do it. Okay. So you just went to Paris. Okay. I guess this is a European-style application, to quote Sarah Palin. Sorry. And you have a sort of GPS-coded triptych with multimedia, all kinds of really great stuff. You just recorded your trip, and you loved it so much you want to just make it available to everybody who wants to go, and you don't want to pay for it. You don't want people to pay for it either. If I'm going to Paris, I want to be able to find this and use it. And if lots of folks are interested, so I inject it into this cloud, and if lots of folks are interested, well, it replicates to serve all these users, and it's also geocoded somehow that when this user picks up this application, it's delivered from a node that's close to that user. They're walking through Paris, they want to get this in a fairly rapid way. Okay, and in the wintertime, when maybe Paris is less desirable, the thing sort of fades, or it descales. Okay. So what this is gaining us is, in the case of the dispersed data, we move the computing out closer to where the data is. And in this case, we're sort of selecting resources that have locality with respect to users, okay, and can give them good performance. But we don't want to lose the cloud paradigm. We like We like the abstraction of the cloud. Okay, we like the fact that you pour things in, something happens, and you get something out. We even maybe would agree to say, well, you should be able to program Nebula applications like Azure applications or EC2. You know, that's still something we're discussing as to how do you actually program into this environment. But it gives you some of the same cloud features. You get scale up, scale down. But what we give you is more geographic sensitivity or locality. We'll execute where the data is or close to the data, and we will also serve the user close to where they are. Okay? And for application groups or users that just don't have the money to monetize their services, it's potentially a way for that to happen. Even if we were to compensate volunteers, we could do it at an order of magnitude less than what EC2 charges. That's been studies that show that. If I just pay you for turning on your computer and joining my network, pay your ISP cost, your power, the depreciation of your machine, I can do it at about an order of magnitude less than 10 cents an hour, whatever EC2 charges. However, you have to be able to live with somewhat weaker performance and robustness requirements, particularly if these are volunteer computers. Okay? Certainly in the case of some of these applications, I mean, if you can't get, if you lose a blog or you can't get, you lose a node delivering this Paris triptych thing, it's probably okay. So we don't know how strong we can make performance or robustness in this model, but there are services that can live with that, and they might be attracted to this kind of model. Okay. So going back to our original cloud picture, we have a Nebula instead. Okay. I don't know that the other Nebula groups have that cool picture. They might. So here our computing is dispersed and lower cost and has greater locality. Okay? And the key to make this all work is we have these network tools that can tell us about this locality. We don't get it magically. We have to figure out what are the right resources to use. Okay. So we're currently, I mentioned you could build Nebulas using CDNs or volunteer resources. We're currently using volunteer resources to do this. Okay. A question we're often asked is, isn't this just grid computing? This sounds like grid computing. And we reply by saying, well, there's different requirements. Okay. So in a Nebula, this notion of collective performance is very important. Okay. If I'm doing blog analysis, it may be that I want to analyze 100 blogs. I want to get the answer back in a bounded amount of time. Whereas if you know the at-home projects, they're just compute forever. They just kind of keep going, and there's no notion of collective performance. They just sort of deliver results. They dribble them out, however they get dribbled out. Okay, in many examples, they don't have a notion of how do you collectively bound worker behavior, worker performance of the volunteers. There's not much notion of context awareness, locality in the at-home. The nodes are very independent. For the kinds of things we're envisioning, there might be a high degree of context sensitivity or locality requirements. Okay. And finally, in terms of state management, many at-home projects are fairly low state, or whatever state there is at the server. To represent sort of cloud applications, there's likely to be much more state that you need to maintain. So it's a lot of interesting research issues. How do you maintain shared state across volunteer resources? These are some really interesting research challenges. How do I get that that convenient state sharing, but across a more distributed pool of nodes? Okay. This is hot off the presses. So we told the grad students. Is this a good idea? Before we spend any effort, just build an application and do it in EC2 and then do it on Nebula, a Nebula testbed, which in our case is Planet Lab right now. And so they did. They collected a bunch of blogs across the internet. So we have a very large data set, and we can then distribute them however we like across our Planet Lab testbed to emulate the internet. And then what we say is, okay, the centralized cloud model would say you got to pull them all down to one place, one site, compute on them, get an answer. With the Nebula case, we find nodes that are near those data sources, and that becomes our cloud. Okay, actually, our cloud is everything, and then we just pick the nodes that are near the data sources, and then we see how well does that do. We didn't quite get around to EC2, so the student has emulated EC2 by just picking a site that had central resources. Okay. So in Planet Lab, University of Chicago, Illinois has 4 nodes that are all in the same domain. So that becomes our EC2. It's just a local. They're all available. Versus Nebula, which has nodes sprinkled all over the place. Okay. Okay. This is not to be overinterpreted. So here we're showing the time it took to process, I guess, probably 1,000 blogs, and how long it took to process 25% of them, 50%, 75%, 100%. So we're showing sort of incremental time, and this is the final time when everything's finished. Okay, and so the Nebula results indicate that by picking compute nodes near the data, okay, we can do better. Right? We can really speed up that type of processing. Now this is maybe slightly propagandistic, I don't know. This is not a thorough evaluation, just to give you a sense of what's possible. This is really bad because one of the blog nodes that was picked happened to be somewhere in Europe with a bad network connection. Just happened, but that could happen. And so the final 25% involve accessing that particular data site, and it's pretty bad. Okay. Whereas our Nebula had a node kind of in Europe that was kind of in the same domain, or not the same domain, but nearby, that was actually able to, not experience that bottleneck. Okay. So this is maybe showing what's possible. Maybe this is sort of like the best case, what you'd like to be able to show. Okay. So the times that we're showing for the Amazon is where it has to pull everything down, then it computes. Okay. But it's paying a lot of network overhead to do that, versus doing it more distributed. Same number of compute nodes, we're not cheating in that respect. Okay. So this is very early. Okay. And we're currently building it. We're very early on in sort of designing a system architecture for this, where application groups can load services into this, and we can begin to experiment. There's a lot of research. So the fun part about this is why, of course, we're doing this is that it's not easy to do. There's a lot of fun scientific work that has to happen. I just briefly sort of mentioned some of the efforts. So, a lot of this is very high level. How do you, what services do you need to provide to applications so they can take advantage of this? How do I deploy a blog service? So I've got blog analysis code. I'm in social sciences, and I want to use this. What do I need? What services do I need? Okay. What are the right abstractions for taking advantage of these environments? So open question. We've made a lot of progress on the system services. But how do you do this? I mentioned the networking already. Proximity or locality estimation is very important to taking advantage of this. So we're doing some work in the network area. If we're using volunteer resources, this issue of failure becomes really important. So how do you tolerate failure? How do you build consensus when things fail, if they fail? And we've done a lot of work in this in the past in sort of other contexts, but we think this is also a very ripe area. So my Nebula very likely will have replicated computation to guarantee that it actually finishes, right? Because nodes could pull away or fail. How do you do that efficiently? And sort of finally, how do I, discover proxy nodes or the right one, or discover volunteers that are best suited for my Nebula application instance or my proxy, or a proxy that I need? Okay. Out of the sea of nodes available, how do I discover the right ones? That's a tough problem. But we're making, we have some of the building blocks in place with the network tools, and what we really have done today is just sort of show the promise of the approach, rather than it's not something ready to be delivered to somebody's desktop. It's more showing the promise. Because the way we do things is we convince ourselves there's something to be gained, and there seems to be. So then we have to figure out how to make it widely usable and how to package it up appropriately. Let me now talk about, there's always other issues in this large space. Let me not say much about incentivizing and security. These are big issues. I'm happy to talk offline about those. Okay. Just a few minutes over, but I started a few minutes, so hopefully that's okay. Okay, to summarize, cloud is very exciting. We believe in it. However, we see some trends that are not well aligned with the current cloud paradigm as we now currently see it. I have to point out, though, that cloud vendors are not unaware of these things. So, I just met with Raghu Ramakrishnan at Yahoo, and Yahoo is building a proxy network. They are aware of some of these issues in terms of the users are sort of left out. Okay. But we're going, full bore after these problems. So we see the presence of large dynamic distributed data as something that may not be amenable to the current paradigm. The fact that we have users that may be mobile, okay, and the fact that we might want to couple applications across different clouds. And I certainly wouldn't hold my breath for cloud vendors to be partnering and providing high bandwidth paths between clouds and having sharing relationships. I don't see that happening anytime real soon. As these guys are fighting for market share, I don't see that as any time coming around. So just to restate, so our vision of the cloud is we're one in which we can provide locality for users and data and between clouds, which again is not well supported in the current paradigm. And we presented two ideas on that spectrum of solutions, something a little bit less disruptive where clouds stay as they are, and a more radical approach. Okay, and even a more radical approach we think is complementary. Okay, it's going after applications that might better fit that model versus the centralized model. And so if you're interested in this work, just going back to here, there's just a treasure trove of research challenges of systems research to do, applications research to do, and you guys are smart people, and we cannot do it alone, that's for sure. So with that said, thank you for listening, and I'll be happy to take any questions.
Questions?
I
Yeah.
have a few questions. The first question is, what's the big difference between the cloud computing and the traditional grid computing?
That's a good question. I'll answer it the way Rich Wolski might answer it, which is to say, we wanted to understand what cloud computing was. We're hearing a lot of buzz and excitement, and so we wanted to build something researchers could use. And so the consensus seemed to be the cloud was what Amazon was providing, okay, which we would say is a pay-as-you-go infrastructure. And in the grid is a fairly different model. I would say the grid is more distributed, typically, okay? It's not a pay-as-you-go model. And, I mean, the cloud is sort of evolving, but I would say those are the two distinguishing characteristics. It's distributed. Probably the initial set of applications, I mean, the cloud does not pretend to be high performance, although I think people want to explore whether HPC in the cloud is sensible to do. And I think it's the monetized nature of the cloud, at least currently, that sets it apart. Others might have other. Jonathan, do you have your own spin on that question?
That's good.
Okay. Your second question?
The second question is, you listed a few challenges that are very good. And do you think that the current computing platforms, such as hardware, like Intel and AMD, they can provide a better architecture or hardware platform for the computing? So your listing the challenges are always for like network layer. But do you have any ideas for processor designers so they can provide better features? Like if you say, maybe reliability is more important than better.
That's a good question. I'm not a hardware guy, but I think, I mean, certainly the emergence of multi-core is very synergistic with this. So right, the challenges I wrote down address more the distributed nature. Okay? And I wasn't arguing distributed because we needed more computing power necessarily. It was the fact that the world is distributed, so you have that. So speeding up architectures are not necessarily going to make those things go away. But I think it's certainly true that clouds have certain constraints in terms of financial constraints, energy consumption, and I think we could all benefit by energy-efficient computing. Okay, so I think that that is certainly a push for clouds, is getting more bang for your watt. So I'd say energy is one of the big things. Yeah.
So you show your proxy networks deployed over parallel lab, and you show some improvement of regions. And does that mean you really employ real application software over those your proxy networks, or you just pour some data without destroying this application and see the improvement?
Well, to gather the network statistics, we have a combination of probes and some other techniques, which are application. I mean, it's user-level probes. That's what your question is, but they're not application specific. To gauge, to get a sense of the network performance. Yeah, but from an endpoint. Now, we're not measuring the actual link level utilization. We're measuring from what a probe would see. Okay, so essentially sitting on top of TCP. What does it see?
Because you show us like kind of different kinds of applications or examples of applications over the proxy networks, but I wonder whether you really deploy that application software over the proxy networks and measure the performance.
Yeah, I showed you two things. I showed you basically the dashboard results, which are not application. Okay, network statistics that the endpoints would see. Okay, the other results for montage and for other, we did utilize the proxy network. So we basically the proxy essentially. So instead of communicating between two endpoints, say in montage, two components of a workflow directly, we insert a proxy node. We pick a proxy node, and the TCP connection runs through the proxy node. So we are using the proxy network in the results that I showed you. But right now it's fairly hardwired, and the proxy we picked, we simply show results for different proxies. The goal is to really enable at runtime to select the proxy that we estimate can accelerate the application. Okay, and results that I didn't show you all the results, but what's appealing is some of our measurements, we can identify proxies that have very stable performance. So these are good candidates to consider. We don't want to overreact to a proxy that all of a sudden has great bandwidth but usually doesn't. So we found a lot of nodes that have better performance and stable performance, and those are the ones we would like to use. So that means that we can use historical data, is what that means. If the results are fairly stable over time, then using past is a fairly good predictor.
So one last question.
Adam.
So for your experiments, you're using Planet Lab as a test bed. And from what I remember, it's just universities sign up, and they make available maybe 10 to 100 resources.
It would be nice if they made 10 to 100 resources.
It's usually less than that.
It's usually a couple.
So when I think of the cloud, I'm thinking like maybe Amazon, has like 10,000 resources available,
right?
Or some huge number. So have you thought of how you can eventually scale up and test on such a large system, or are you still at like getting at the ground level?
That's a good question. So running on a few hundred nodes is not the same as running on thousands. Although Amazon, I'm not sure who is actually running on thousands of Amazon nodes. You're limited to 30 VMs per account in EC2, but I suppose you just create a bunch of accounts to get more. So our real goal is to move off of Planet Lab, and so I showed you this Nebula thing. We have this thing called Nebula Central. We're standing it up. It's a place where we can attract volunteers. And Dave Anderson at Berkeley said, we might host it on the BOINC website. It's something that they're entertaining. So you're asking the right question. We don't think 100 nodes is scalable. It is evidence of scale, so we would certainly like to expand that several orders of magnitude. And we need real volunteers to do that, and that takes a lot more effort and infrastructure to attract those.
Okay. Yeah.
So that's the plan, but we are just getting started.
Okay.
So.
Future Okay. Let's thank Jon once again for a very nice
Thank you.